Hi everybody, and thank you for attending this small tutorial and small workshop on Vedo. So Vedo is a relatively recent Python module for scientific analysis and visualization of 3D, but also 2D objects. So why does it exist? Why do we need it? Well, when it comes to 3D, Matplotlib, I would say, is not maybe the best tool we have. And for 3D, we have actually other fantastic libraries like VTK. And actually Veda is based on VTK. But VTK has, I would say, quite a steep learning curve. And well, for example, if you wanted to just create and visualize a simple cylinder, you would have to write quite some code, and which involves the rendering parts, the creation of the object, etc. Whereas in Veda, this is quite straightforward. It's basically a one-liner. You import Veda, the library, and then you create the object and you show it, and that's basically it. So in the scientific pipeline where you acquire data, then you make some post-processing, and then you finally write your paper. Where does it sit? Where does Veda belong? I would say it belongs more on the post-processing parts of these pipeline, where you already have some reduced data set that you want to analyze and maybe visualize and then produce quality renderings. Definition I like for Veda is, I would say, a 3D powered version of Matplotlib for sure, and a handy day-to-day tool for the researcher. And it can prove useful with any type of data having a spatial or temporal structure. So what do we do with it? Well, you can work with polygonal meshes and point clouds very easily. You can do morphometrics, warping meshes, deform meshes, cuts, and find connectivities, and all these sort of things. You can also do analysis on volumetric dataset, 3D stacks like tiff files, etc. And also in tetrahedral meshes. It has 2D and 3D plotting and histogramming capabilities, and it doesn't live in isolation. It's integrated with other external libraries like PyMeshLab, Phoenix, and many others. It offers a command line interface for quick visualization. You can export and exchange 3D interactive scenes to file. You can create animation, create interactive graphic user interfaces. And finally, I think you can really produce publication quality outputs. And do it so you don't lose access to the native VTK classes, the visualization toolkit software. So that at some point, if you find that something you cannot do with Veda, you can still go back to the VTK classes without ditching everything you've done so far. Okay, so next point. Okay, so how do you install it? Well, simply with pip install Veda. You can find documentation at this link. I think I have it. Sorry, I have it here. This is the web page of Veda. You can see you can embed 3D images into the web page, for example, and basically Veda is thirds, at least as for what regards to documentation, as example based. So you have something in mind, you find an example that resembles that what you would like to achieve, and you start from there. You start building from there. So you have a whole number of examples, from basic to more complicated ones, and we got volumetric data sets, or even plotting, or many other things. And it's quite a large library of examples. Now I think it's more than 350. And so, for example, if you if you want to find something related to, I don't know, mesh, you just type in mesh and you get the example that contains that specific keywords. Okay, so let's continue. Yes, all the examples are designed to be short and intuitive. Most of them are less than 30 lines. They're searchable, as I showed, and they're also runnable. If you, from the command line, from the terminal, you say vedo dash run an example name or part of the string that is contained in the file name, you get the specific example run. Maybe I can show you one case. I don't know. Well, the first example would be building a mesh. So if we do vedo minus run build mesh, let's see if it finds it. Yeah, it finds two, so you have to specify more, build mesh. And so it should now pop. So you get a dump of the code and you get the output. Okay, so move on. As I said, yes, you can quickly visualize things, like, for example, if you have a mesh, or maybe this is more interesting, if you have a tiff stack. Sorry, I want to select this, see, and then I just copy paste this in here. So it downloads automatically the file, and then it shows this is a volumetric stack, so it shows by default the isosurfaces given a threshold. So you get a slider and you can slide through different threshold values. This is just from the command line. Okay, also you can visualize entire scenes, complex scenes like this one, for example. And again, it gets downloaded on the fly, and then it generates a brand new 3D scene where you actually can interact with these objects. So, for example, you see you get flags when you hover with the mouse, and you can zoom, and you can, for example, remove parts of it, etc. Okay. So next. Yes. So as for for the command line interface functionality, you have different modes, and you can visualize the same data set in different, like slices, for example, or with ray tracing, or with XY slices, and so on and so forth, also from the command line. So I showed you already before this one example, but I go back to it and see it again, break it down a little bit more, and see what it does, what it really does. So here we want to create a polygonal mesh, right? A polygonal mesh is made of polygons, and polygons are defined by vertices and faces, right? A polygonal mesh. So you define a set of vertices in space, and these are the coordinates of these vertices. You define faces. For example, the first triangle would be formed by point number 0, 1, point 1, and point 2. So these first three. And then the second face would be point 2, point 1, point 3, and so on and so forth. And then once you have these as lists, you just give them to the mesh object as in the init arguments, and you get a vedo mesh object in return, and you can now do whatever you like with it. You can define colors, you can do many things, and I will show you a few things you can do in the next examples. You can also define labels for the mesh. For example, if you just want to know which vertex is which, for example, you see that vertex 0 is this 50, 50, 50, and in fact you see it corresponds to the coordinates, and so on and so forth. So it attaches labels to the vertices. You can retrieve them as an NP array, and finally you show them in one single go. So you say show mesh labels and with axes. You have different types of axes, and one is just this specific type. Okay. next example would be, yeah, as I said, you can do coloring, right? You can encode information into a mesh, either by attaching this information to vertices or to faces, right? So in this example, what I do is to define a plotter, which is basically the windows, the rendering windows that you have seen before. And actually, you can do something interesting here. You can split into two parts. Most of the time, you want to compare stuff, right? You want to see what changes when doing one thing or another thing, and you want to see both at the same time. And this is how you can do it. So, for example, we define this plotter that has two sections, two parts, two sub-windows, say. And then you define a mesh. You create a mesh from now. It's not done manually, but you just load an existing file, and then you define scalars. For example, you define that you grab the points, the vertices. You take the z coordinate of them. You can do some other operation, and then you have a numpy array that corresponds to these values. And then you say that you want to C-map to color map with the hot scalar map and color map. This is the same as matplotlib. This set of scalars, and you do it on the vertices, on the points. And you can do it at the same time for cells, for faces, for the polygonal faces, and in this case you grab the centers of each face, and you do very similar thing. And you want to, for example, use a slightly different color map. Maybe you add a scalar bar, and then you do this. You grab the window, and you say that at the first renderer you want to show this, the first man with first coloring, maybe with some text, and the second one you show the other thing, and that's the results basically. So you see it here, maybe here. Well, I can just run this, and you will see the results here. So the two scenes are synchronized, so that when you drag the mouse, both are changed in sync. So that's the default behavior. Okay. Next example I would like to show you. Well, having these meshes is maybe not not very interesting so far. What we want to do maybe is align them. We want to cut them. You want to modify them, and you have a whole set of tools for doing that. The one that I'm showing you here is the so-called iterative closest point approach algorithm, and it works by choosing every time a set of closest points and then trying to match those points by scaling the mesh or rotating it. So again, it's very easy. You load some data set, some model. In this case, actually, these are shapes from the growing mouse limb. So you have a different ages. So let's say you want to align them. Well, as I said, you first load them. You make a copy of the second, and you align to the first. And you say that rigid is, you don't need the alignment to be rigid, so it can be scaled. And then you define also color for it. And that will be stored into align to. Now, you want, for example, say, okay, now I have aligned them, and I want to know how much distance is the resulting alignment to the original target shape. So you use this method, which is called distance to. So you say align to is distance to the target, and then you decide that you want to color map these distances in the green color, and you add a scalar bar to it as well. Maybe I can show you this on live, so you can see, and it's very fast. So let me. Oh, that's it. So you see, you have the original mesh. The target is in this yellow gold color, and the resulting alignment is shown here with the color map. So, for example, the points that are most distant from the target are have a higher, a darker green color. Okay. This is one thing. Next example is, for example, you want to interpolate data, right? So you have a mesh, and you know, for example, that this mesh has specific values at specific points, and you want to extrapolate what would be the value on other points which are close by. And you can do that as well, obviously, with few commands, with the command interpolate data from. So breaking down this example would be, it's very easy. Actually, I can do it here. Maybe it's more visible. So you import what you need. You load the mesh. You define a number of points. Just for simplicity, I just pick the first 100 here, right? And I just give them random values just for the sake of the arguments. And then I create a set of points with this scalar value, right? So I create points, I define a radius for these points, and I column map them with the rainbow column map. And then what I say is just take the original mesh and grab the data that is contained in points with the 5 closest points, right? And I give it the same color map, and I finally add the scalar bar. And that's basically the result of it. I just run it quickly, and so you can show, I can show you better what it looks like. Yep, there it is. And yeah, you see that points of the mesh which are close to the point with a known value are kind of the same color as the point, right? This is what should be what we expect. Go quickly to the next example. Yeah, one other cool thing that you can do is to modify your mesh. Maybe not simply cutting or editing, but just really warping, changing its shape. And again, you have a few ways of doing this. The one I show you here is based on a tool which is a mathematical method which is called thin plate splines, and in Veda it's called just warp. Okay, for simplicity. It does what it says. It warps a mesh based on a few points that you want to move. For example, say that all these points in red should stay fixed, but one point here should move to the right. And basically, you define these points, you give them to the function, which is called warp, and that does the job. Right. So maybe I show it here again. Yes, this is an example. So let's forget about these details. So you load the mesh, you decimate the mesh. So you subsample the mesh. You define as a much smaller number of points, which still constitutes a polygonal mesh. And then you define a number of source and target points, and the one that should not move. Right, so these should move and these should not. You create some errors that connects these two sets of points, and then finally this is basically what does the job. Right? You grab the mesh, make a working copy of it, and then warp based on these movements that you defined. And the rest is just basically visualizing the thing. So I can run it for you, and yeah, and then you get the result that is shown. Okay. Good. As I said, polygonal mesh is not the only object that you can work with. You can work with 3D images as well, tiff stacks and all this. It's a set. You can use many different formats. You can do analysis on these volumetric datasets, and creating one is very easy to start. If you start from a NumPy array, right? Well, obviously you can load any file, but if you have a NumPy array, you can already directly transform it into a Veda volume, and that's how you do it. Again, maybe I'll show it here. So you define a NumPy grid. I'm probably familiar with this if you use NumPy. And then you define a scalar field, right? At each point in space, you define that, you say that you associate a scalar quantity. And once you've done this, this is purely NumPy, you define a volume, initialize volume with this scalar field, and it creates a volumetric object. And now you can go back to NumPy if you wish, after having done some analysis or whatever. And also you can visualize it in various ways. For example, visualizing the voxels using voxels that, for example, have a minimum value of 1 and a maximum value of 2. Right? And you column map them with some column map you like. And this would be the result. And you do it in two sub-windows like before. Right? So this is the original volume from the NumPy array, and this is the thresholded, if you like, volume, where you only see voxels that are between, whose value is between 1 and 2. Okay, let's move on. Yeah, so this, sorry. Lost contact. 1 second. Okay, sorry. Next thing. So obviously you can do 3D images. You can do also 2D images easily. You can in Veda you can crop, resize, compute fast Fourier transform, compute gradients, and all these sort of things. You can also treat an image, a 2D image, like a mesh. You can transform it, and this way you can morph it. For example, you can do interesting things. For example, in this case, what we did in the lab was taking pictures of gene expressions, and now you have a time course that you want to map to associate a specific time point to a specific gene expression. Right? So you have a mesh, and you want to know for each of the nodes of the mesh what is the corresponding gene expression, and you can do it easily by morphing to adapt the photographic limb, in this case it's a mouse limb, to this ideal time course. So, and for this you need warping. And this is what is done here. As another example, you can do, if you have, again, a photographic image, and you want to know what is the intensity, for example, over a path. In this case, the path is a set of rays starting from the same point, the origin. You can do it the same way. You can probe your image with these paths. And you can do all sorts of statistics here. And you can see actually that in Veda you have a nice thing that allows you to plot. It's integrated. It's a plotting capability which is integrated into the package. So you can do interesting things with it. And in this case, you just sample the intensities and you just create a plot that contains these all the intensity along the rays and the average, and their average value. Okay, maybe I don't need to show you this here because it's pretty obvious, I would say. The other thing which actually I'd like to show you is that you can also interact with the scene in various ways. For example, you can have buttons that triggers events. So for example, you can have some rectangle shown here that you click and then something happens because a function is called, or even the same mouse. When you hover the mouse, you can attach a calling function, for example, and this is what is done here. This I will run it. Let me check which one is this. Yeah, it should be this one. So, for example, let's go quickly through this. But maybe first I'll run it so you see first what it does. So as you see, as I move the mouse, you see something is happening. And what's basically happening is that you update the position of a set of points, right? So, and you see the code is very easy. To code this is really 24 lines of code. I mean, you define a plane. Let's start from there. From here, you define a plane, which is the gray plane that you see here. You define a line. You define nodes, which are the points, the red points you've seen before. Now you define a plotter object, which is the window, and you add the callback. Right? As the mouse moves, please call this function. Right? You don't need all this, but just for fun. So every time the mouse is detected to move in scene, this function is called, and what it does, it checks what has been picked, and basically what it takes the coordinates of the points and it just modifies them according to some rule that we don't need to understand now. But as you see, it's very compact and very straightforward to do. Yeah. Okay. What I'm showing here is a real-world application of this in the lab. In our lab, we are studying mouse lane development, and what we do is well, we do many things, but one thing we do is to use cell clones. What are cell clones? You can have a cell which becomes fluorescent, and as it divides and the tissue grows, its daughter also are fluorescent, so they leave a sort of trace that shows that can be hint at some mechanical properties of the tissue. So we have many limbs and we have many clones, and this is actually a tool that shows how to not only browse the dataset which is available to us, but also measure some properties of these clones, like the point clouds, for example, the volume they occupy, and all these sort of things. And you can do it interactively, and I can show you here the application that does it. And it's basically, it might look very complicated, but it's actually not so complicated. It's, in terms of code, it's like 200 lines of code, more or less. So you can interactively pick one specific item, and you can inspect it in a 3D window with photographic images, and also maybe a big and busy one. And also things like number of cells that you have, the volume they occupy, and some other properties like some statistical significance, and this sort of things. And it has been quite useful for us in the lab. Okay. So, and actually, yeah, as I say, you might think it's very complicated, but actually the bare bone version of the previous is just 30 lines of code. It's just define what happens when you click on one window, one of those small windows, and basically splitting the rendering in a number of parts. So, and we have an example for this in the Veda webpage. So last thing I would like to show you is a bit of resume of 2D and 3D plotting capabilities of Veda. You can plot, do simple things like histogramming, and to more complicated things like glyphs, which represents direction of points in space, different population of points, fitting to to points with error bars. And I would say, obviously, you can do all these things in Matplotlib as well. But I think one added value of this is that being the approach completely different. Sometimes it turns out it's very easy to do things which in Matplotlib could be extremely difficult to do. For example, something like this would be very, very difficult to do, but it's really easy in Veda. And with this, I think we can go to our conclusions. The Veda library is now, I think, in a reasonable good state for general use. It has proved extremely useful for us in the lab for many applications, and I'm definitely happy to offer support for those who would like to give it a try. So thank you for listening.